Hello, this is Darko, and today we will be discussing causal inference propensity score matching. It is one of the causal inference approaches, and we will go deep into various angles related to propensity score matching. But before I start, let me just say a few words about the format of this podcast, or a word workshop, I would say, more like a workshop. Uh, so the format is really interactive. So you may uh, ask any questions in the comments at any time during the podcast. So it can be right now in the middle of the podcast, or even after the podcast, whatever is more appropriate, what makes sense to you. You can even send me direct messages on various topics that you might want to discuss further on the podcast and so on. Now, back to propensity score matching. Why is propensity score matching? Why would we use it? Why is it so interesting for many causal analysis approaches? Well, first, it is one of the causal inference approaches that enables us to do causal analysis when we have no experimental setting, so in a non-experimental setting. Most straightforward study designs in causal analysis in general involve setting up the experiment so that the experiment itself would define a causal estimate, some causal relation that we want to observe and measure. But it's more difficult to do that if we don't have an experimental setting. For example, if we don't have randomization in the experiment, we have just observational data, and we want to draw causal conclusions from it, then we have to use special statistical approaches. One of them is propensity score matching. There are others, like inverse probability weighting, instrumental variables, and so on. But today we will focus specifically on propensity score matching. So propensity score matching is actually one of the most in-demand approaches today. Why? Because most of the data out there is actually observational data in the world of data science, biostatistics. Propensity score matching is used in various fields. One of them is healthcare, so real-world evidence. That's really where I come from, so I have most credibility to speak there. So real-world evidence, external control arms, and many other life science settings. But propensity score matching can be also used in marketing analysis, so causal analysis in marketing, A/B tests. It can also be used in various other fields such as genomics, bioinformatics, differential gene expression, and so on. Today I will mostly focus on this healthcare angle, as I said. And the first question that comes into focus is, what do we achieve with propensity score matching? So this is actually one of the interesting topics, and I will present it using an interesting example from here. So let's just start with a clean starting point, a clean slate for causal inference, the most obvious paradigm where we have the cause and effect. So we have the cause, we have the arrow that goes to the effect. It's kind of a well-known, well-established causal paradigm, even though it doesn't always have to be like that. But let's start with it for now. If this cause and effect were isolated in an ideal world, it would be very easy to measure the causal effect. But in the real world, as we all know, things are a little bit more complicated. We have so many things that can influence our analysis. And in the setting of observational data, real world evidence, for example, number of things that could influence the analysis is generally present, both in the things that we can see, that we can observe, but also in variables and factors that we cannot observe and cannot measure. So I'm going to now add another box here to illustrate why this is important. So let's say we add a box called C here, just C. What does the C mean? The C is a confounding variable that in theory, this confounding variable can complicate things for us. Why? Because confounding variable could be related to the effect, but it could also be related to the cause. And this is a very frequent situation in the real world around us. So what does this mean for the analysis? Because the confounding variable is related to the cause and the effect, the causal effect that we previously saw was much easier to estimate. It's now much harder to estimate, and it could be distorted. The analysis could be distorted, and the effect that we are actually seeing could be nothing but the confounder injecting its effect so that it's actually not the real causal effect. It kind of transfers it to the cause and the effect, and we can measure something, we can measure some effect, but it's not the real causal effect that we are interested in, the direct causal effect between the two objects in this case, which are the cause and the effect. So to cut the long story short, if there is a third variable associated with both cause and the effect, it could distort the causal analysis. In fact, this confounding principle, and usually there isn't just one confounder, there are many of them, is the main thing that prevents us from doing causal analysis on observational data. Now, where does the propensity score matching jump in? Very simple. We can actually break this principle that I'm showing here by, for example, removing one of these arrows. And therefore, it would be easier and more realistic to measure the actual causal effect. Why? Because it doesn't have a backdoor. So we call this the backdoor principle. If I leave the situation like this, the relation between cause and effect, which is this arrow here, could be distorted by the fact that the confounder C is injecting some information through the cause, through the back door, into this relation cause and effect. So we have a distortion of cause and effect relation. Why? Because there's a back door for cause in this case. So it's simple. We remove the back door. We now have a non-distorted causal estimation between cause and effect. Why? Because there are no back doors. Only the cause could be causing the effect, right? So there's no back door. If I put it back, it's now we have the back door again, difficult situation. The causal effect that we estimate could be distorted. So propensity score matching is used to remove this back door. Other approaches like randomization in, for example, randomized clinical trials or randomized experiments in marketing, they also remove the back doors. And some of them do it better, some of them do it worse. We also have the instrumental variable approach. That will be a topic for another occasion. Now let's focus mostly on propensity score matching. So we want to remove the backdoor. In reality, the situation is pretty much like this. You don't have just one confounder. You have multiple of them. Like you could have 5 confounders. And each of them could be having a backdoor towards the cause, but also towards the effect, right? It has a confounding arrow towards the effect, but the arrows that we can influence are mostly to cause. So the back doors to cause, and I will soon explain why. So it takes a while until I actually sketch this, but you get the point. It's more complicated than just having one confounder, but effectively, if we remove, I could now finish for this one as well, but not gonna do it. You get the point. If I remove the backdoors towards the cause, even though there are associations between confounders and the effect, the cause is clean. It has no backdoors. If I removed all of them, I can now proceed and do causal analysis on observational data, real-world evidence, external control arms, and so on. Now you get the point. Why would we use propensity score matching? But propensity score matching is a much deeper topic than just understanding a schematic like this. A lot of people use propensity score matching without actually understanding it, without understanding how it works, or even what it is. A lot of people don't even understand why do we use the term propensity. So what is propensity anyway, right? Why do we call it that way? It's interesting that the propensity is actually nothing but a second name for conditional probability. So propensity is really a conditional probability of being treated, or in other segments, non-life science segments, conditional probability of the intervention, which is pretty much the same, just in different settings. So conditional probability, that here we can use this formula, and don't be intimidated by this formula. It's actually very simple. So conditional probability is nothing but a probability of being treated given some variables. These variables could be demographics like age, gender. They could be biomarkers. They could be disease scores, lab scores, or any other variables that we have in other fields. So basically, we are trying to estimate probability, conditional probability, that the patient, in this case, will be treated given demographics and other variables, in this case. And that probability is basically this formula, represented by this formula. That's what we call propensity. So propensity, in other words, is actually a probability. That's very important to understand. Probability goes on a scale from 0 to 1. So propensity, when we calculate it in studies, will also go on a scale from 0 to 1. Now, how do we estimate propensity? That's another question. And here is another very simple explanation. We basically do regression, right? So we put the variables that we want to include in the model. These are usually the variables that we observed. So propensity score matching is characterized by the fact that it's very dependent on the variables that we can observe and measure. Now, this is extremely important. I will mention that later. Why? For now, let's just keep this in mind, that the variables that we measure, we can use them to create a propensity score model. How? Well, the independent input variables will be some of these measured variables like gender, age, disease score, biomarker, etc. And then we can create a regression model in which the output, or the prediction, the probability output in this case, will be whether the patient is treated, how probable is the patient to be treated, how probable is the patient to be not treated or be in the control group. So very simple. We have the input variables. We have information whether the patients are treated or not. We can create a regression model to output the probability using logit or probit model, for example, to output probability of patient being treated. That probability, that's the propensity. Very simple. Now, it's important to say that Regression models are not the only way to calculate propensity. We can also use machine learning, AI. That's a whole other story. But really, regression, probit logic, is the most standard way we can use to calculate propensity. The question is, what do we do next, right? So when we calculate propensity, as I said before, propensities are from 0 to 1. That's the scale. So you can see here the numbers. Let's say the boxes are one group of patients, let's say treatment, and the circles are second control patients. And they all have their propensity calculated. So now we can play a game. How do we match them? Well, let's say I want to match this patient with propensity of 0.55 with another patient, and I will search for the closest match, which in this case is 0.5. I can do the same for 0.9 from the left group. Oh, I have another patient here, which is exactly 0.9. So you see, we are equalizing the propensities for patients and matching them. For each patient, I'm finding a match that has as close as possible propensity to the patient. Sometimes it's not possible to do an ideal match. So for example, in this case, I have 0.12. The best possible I can do is 0.1, which is very close, not identical, but very, very close, which is still okay. And in propensity score matching procedures, we can set how much freedom do we want to allow when matching patients. There is a term called caliper, and we often set these calipers to be smaller or wider depending on how much accuracy we need in the analysis. So if the caliper is smaller, the matching will be tighter, but more difficult to achieve because the matches will not always be achievable. If the caliper is wider, then we will have more matched patients, but they will not be tightly matched. There will be some freedom in that matching. Now, what's very important to understand is that, we could theoretically continue with this process. I could try to find the closest match to each of these. And effectively, what I would be left at the end is the fact that some of my patients will actually not have a match, right? So I found all the matches that I could, but now some of my patients don't have a match. And this is another characteristic which is very important for propensity score matching, which is that sometimes a number of patients or a part of the sample in other fields is discarded. And we use the term trimming in statistical sciences. So trimming and discarding patients can introduce a variety of problems in causal analysis and in statistical analysis in general. That's why it's important to mention this right now. I will be going back to these problems at the end of the podcast, but for now, it's very important to understand that trimming can be a caveat and can introduce problems with unmeasured confounding. There is a paradox called the PSM paradox, which I will also explain later. So for now, let's just keep in mind that the fact that we cannot include all the patients sometimes can cause problems. So we are solving one thing, which is we're solving confounding, but when we solve confounding, there are the side effects. So we have to worry about the side effects as well, right? Okay. Now, if we were to complete, this was pretty much like a game of doing propensity score matching. In real setting, you have statistical packages that everything that I was doing manually here, there is an algorithm that does all that and governs all that. what happens at the end is that we have an intervention group and the control group where the variables that could be confounders are equalized. So not all of these variables are confounders. Some of them are, some of them are not. But we cannot play a game with it, right? We have to be sure, and we have to make sure that none of them, as maximally possible according to our power, none of those variables that we can correct are causing the problem. So in this case, there are known variables like gender, age, disease score, biomarker, some biomarker. As a product of propensity score matching, they will be equalized to a certain extent, as much as possible. And the fact that they are equalized means that the likelihood of them affecting the analysis as a confounder is now much lower. Now, very important aspect when you practically do propensity score matching, sometimes you have a situation that you did propensity score matching, the scores are aligned, but the individual variables like these are not aligned perfectly. So this happens sometimes because we are collapsing many variables into one. So we are collapsing, in this case, 4 variables into a propensity score. So sometimes the algorithm can find a combination which equalizes the one variable, the propensity score, but doesn't equalize individual variables. This rarely happens, but it does happen. So when you're doing propensity score matching, it's very important to check the variables. Are they equalized to a certain extent? Is there a big difference between them? You have to kind of manually check this. That's what I always suggest. Now, another very important aspect. You see here, there are the 2 boxes marked as unknown. So propensity score matching will enable us to correct for the known variables, potential known confounders. But it's very interesting that it will not help us much, or even at all, with the unknown confounders. So that's the difference between randomization and propensity score matching. Randomization corrects for both known and unknown sources of bias, but propensity score matching only corrects for known sources of bias, which means that now we have this unmeasured confounding, unknown, as a problem, and we have to deal with it. I'll explain later how you can potentially address this problem, but it's very important to understand propensity score matching should rarely be done without a sensitivity analysis covering for the unmeasured confounding and checking whether that unmeasured confounding could be a problem. Now, I'm going to stop here for just a minute because I see there are a few comments which I didn't address. Apologies for that. So I see a comment from Demelash. Great to see you, Demelash. Thank you for joining. And I see another comment by Mohammad. So question from Mohammad is there any way to find and optimize the caliper? Now, there are standard values that often exist in the software packages to use propensity score matching. So you can use various calipers like 0.05 or 0.1. Often they are used as those values, but it's important to understand that those values are not always useful. So depending on the analysis, depending on how tightly you need to control for the confounding, the caliper may be smaller or it may be larger. You can give it more freedom if the analysis allows it. So there's no one number that I can tell you. It has to be decided by interaction between a statistician and a domain expert that tells you, oh, this much difference, it's pretty much the same, or this much difference, we cannot allow this difference, right? So it should be decided on a basis from case to case. Okay. Are there other specific assumptions for using propensity score matching? I mean, yes, other than using it in observational studies, okay, from Demelash, yes, there are numerous others, but observational studies are really the most abundant one. So if you think about it, pretty much all the data that goes out of the experimental setting, most of it actually ends up being some form of observational data. That's why the tag observational data is used so much by me. But there are other places in causal analysis, like, for example, in genomics. We can use it in many fields where we need to correct for confounding. So anywhere where you may need to correct for confounding, the propensity score matching can jump in. Of course, given that you respect all the assumptions, there are other assumptions. The typical causal assumption that you have in propensity score matching is the exchangeability of groups, same as you would have with randomized control arms, and it's mentioned here. That's really the most important one. Imagine if I was to do this, and I just change the groups, and for this one I say that it's intervention, and for this one, the right one, I could say it's a control. So I exchange the groups. If I did everything correctly, the treatment effect should not change. So the treatment effect, in other words, is not dependent on which group I choose. Pretty much similar concept of thinking as in randomization. And that is the assumption of exchangeability. There is another assumption that is very important, which is the assumption of positivity, which has to do with the fact that you have patients stratified in the groups in a way that you cover actually the correct stratums in those groups, that you have a positive value of presence there. There are other assumptions. There are a lot of assumptions, but really for this occasion, the exchangeability is really the one to focus on. And it's the most important one to achieve, even though others are important, right? Others carry their weight and importance, and we will talk about them in the future as well. But to not stray too much from the topic, first let me check other comments. Yes, so there is a comment from Priyanka. And let's go back to that slide. So Priyanka is saying, well, there were multiple patients in one of the groups that could potentially be matched multiple times with one patient from a different group. So for example, I have patients here like this one, 0.9. What if I could now match this patient to this one or this one twice? So I'm going to copy and paste this one, and I'm going to do the same again. So this patient is unmatched. Okay, well, I can 3 times match it to this patient by copy and pasting here. Effectively, using this approach, I could now match more patients which are not matchable by enabling matching with replacement, which means that one patient can be used multiple times to match against other patients. The alternative is that we use matching without replacement. Now, I think, Priyanka, thank you so much for mentioning this. This principle is very important. Why? Because there are characteristics of these two approaches, so matching with and without replacement, that can be very important to address in a causal inference setting. So if you are using matching without replacement, that is kind of organic, right? It seems natural, organic. Each patient is used once, so it kind of feels more organic to do it that way. And we don't repeat a patient twice or 3 times. We don't give one patient more weight in the analysis. Now, because sometimes we cannot have enough patients to do the matching correctly, sometimes we are forced to use matching with replacement, where one patient can be kind of copied. In this case, I was using copy and paste in PowerPoint, but one patient is used multiple times in the matching, and that comes with caveats. So there could be problems with unnatural variance. So when we use one patient multiple times, now we have unnatural variance in the analysis. When there is unnatural variance in the analysis, we could have statistical problems, right? So it would enable us to match more tightly because we will have more matched patients. But it will also cause these problems with variance and a bunch of other problems. So what I typically do is, if I have enough patients both in the control and intervention group, especially in the control group, that one is often the problem, I would go with organic one-to-one matching without replacement. But if there is a problem, like we have less patients in the control group, we cannot do the matching as much as we would want, then we can use the replacement, but we have to be aware of its caveats and perform a sensitivity analysis to see if that affects the results. So that's very important. Now, the other part of the question, Priyanka, is you mentioned one-to-one matching, right? So the matching could be one-to-one, where we pretty much have this organic way of matching, and then we end up with equal number of patients in the intervention and the control arm. We could have different settings. Imagine that we have a very large control arm. So it would be really a shame and statistically not smart to discard a huge control arm just because we want one-to-one matching. We could do 1-to-2 matching or even 1-to-3 matching. It's still fine. And it's better to have a larger sample in the control arm anyway. We could do 2-to-1, various variations, but it all depends. What do we gain? Do we statistically gain a better, more accurate, more objective estimate or not? Based on that, we make a decision. What is the most optimal way to create the study design in that case? Okay, next question. Just one moment. Okay, yes. So by Damelash, is PS a statistical tool by itself, or is it to be combined with other statistical tools in publications? Good question, Damelash. So really, it is really a set of tools. So propensity score matching is a set of tools and algorithms, modeling approaches that we can use to correct for this confounding and bias. But your question is really good. In most publications, it should be used combined with other statistical tools. And we will actually cover them in the proceed of this podcast. So very good question. Just going back before we actually go to that, Damelash, maybe actually it's a very good point to do it now. So two most important problems that may arise when using propensity score matching, there are many other problems we can discuss. You could actually discuss various other problems from different angles, but these are the two top the top list, if I may use that term. So the two problems that come have to do with the fact that I mentioned before. we can correct only for the measured confounding. But what happens with unmeasured? We don't correct for it using propensity score matching, which means it's a problem, right? So that's why we have to combine the propensity score matching with other statistical tools and approaches which will help us evaluate the sensitivity of the analysis towards unmeasured confounding. In other words, we have to quantify unmeasured confounding, we have to address it, we have to check if the analysis breaks in terms of is unmeasured confounding large enough to break the analysis. That if it's not, it's a better situation for the analysis. If it's large enough to break the results, then it changes the whole interpretation of the analysis. So calculating values like E values and Rosenbaum gamma is a way to quantify and evaluate various angles around unmeasured confounding and whether how it relates to our analysis. Is our analysis robust to unmeasured confounding or not? The second problem that may arise, and it's actually well described in the literature, is called the PSM paradox, or the propensity score matching paradox. What it is. Now let's go back to this slide to explain it better. So our goal is to equalize the known covariates, potential known sources of confounding. In this case, it's age, gender, disease score, and biomarker. And let's say we achieve that. Let's say we do a very good propensity score matching. We equalize these variables. They're no longer affecting our analysis. And now we think we can do causal analysis. But there's a problem. Unmeasured confounding, sometimes, it doesn't happen always, but sometimes it happens that as we solve the measured confounding, the unmeasured confounding starts to spike. So there is a paradox. Initially, we started by trying to fix the confounding, but actually we ended up increasing confounding by sometimes a large amount in the space of unknown confounders. Again, this doesn't happen always, so it's not a rule, but it is a paradox that sometimes happens. And propensity score matching is not very valuable unless combined with an analysis that could tell us whether this propensity score matching paradox is actually happening in our analysis. So going back here, propensity score matching paradox, one of the most frequent ways to address it, and it's very often used in the publications, is, and I use it personally a large number of times, is that you combine propensity score matching with another approach, which kind of tries to achieve causality in a similar way, but that you know is not prone to propensity score matching paradox. That it's very, very, very unlikely and unreasonable that that methodology will have propensity score matching paradox. There are a variety of methods that belong into that category, and a number of methods associated with inverse probability weighting, another set of causal inference methods, is much, much less prone to PSM paradox. So very often, to your question, Damilash, you would combine propensity score matching with some weighting approach, because the weighting approaches, they don't trim the patients. They keep all the patients in the sample, which makes them much, much less prone to PSM paradox. And they kind of complement each other. They kind of give us the answer from multiple angles, but causal answers in both cases. And as I said, they suffer from different weaknesses, which kind of makes them a good combination. So I hope that was a answer to your question, Damilash. Thank you. Let me just check if there are other questions. Okay. Again, this is an interactive session, so you may ask a question at any time. I'll just try to stop and discuss in that different angle. What I skipped to answer Damila's question is also another topic which is very important. When we do matching, I was actually playing around with this. I call it the game matching. So what I was doing here, where I was matching patients one-to-one, so each patient, I find the best possible match. That approach is called the nearest matching algorithm. Full name would be nearest neighbor. So these patients, which are the nearest neighbors in terms of matching, we kind of match them one-to-one, patient by patient. So we go patient by patient and match them. That one is the most organic and one of my favorites. So I not favorite because I have some special favoring towards it, other than it is statistically sound and objective very often if you have the data that supports it. But there are others which are often used in combination or even separately. One of them is called the optimal matching. So imagine that if I, just put this back and I didn't go patient by patient, but actually had these two groups, and I still want to minimize, but collectively I want to minimize the difference between them. Sorry about this. So if I took all of them together and all of these together and collectively wanted to minimize the sum of distances between their propensity scores, that would give me a collective lowering of difference between propensity scores. And it's a very effective technique to minimize this difference. And we call it the optimal. Why? Because the goal is to optimally find the collective difference, which is minimal. So instead of going individually, patient by patient, we can collectively minimize the difference. We still use individual patient data, but we collectively, effectively minimize difference. And that's called the optimal matching algorithm. There is a stratified matching algorithm where you basically create stratums. Okay, this belongs to stratum 1, this belongs to stratum 2, and then you can find the appropriate stratums in other groups and kind of try to equalize them per stratum. So that's another approach. Sometimes you can use 2 or 3 approaches at the same time. It's best to triangulate, so to use multiple approaches, let's say 2 or 3 approaches per analysis, because then you can show evidence whether the choice of the approach influences the analysis. If all the analyses point in the same direction, that adds to the credibility to the analysis. Now, okay, so I have a question from Safura. Thank you so much, Safura. What is the basis of weighting? So that's another group of causal inference approaches that I mentioned before, which is less prone to PSM paradox. And it's the one that we will be covering in some of the next podcasts in detail. But right now, I think it's a good chance to discuss what Safura requested, which is what is the foundation of weighting? How do we weight them? Interestingly, we also weight them very similarly as we would calculate this matching here with the propensity scores. So we also use the probability. Is not a conditional probability of patient being treated. So we also use probability. Pretty much the same approach, but you apply it in a different way. Instead of trying to calculate this probability and then match patients, we actually calculate this probability, and then we use 1 divided by probability, so inverse probability, right? So we can inverse the probability, and based on that probability, we can give weights to patients. So some patients will have a lower weight, some patients will have a higher weight. A combination of those weights will allow us to equalize and to equalize the variables as in the propensity score matching. But it's important that we just add weights. We don't discard any patients. That's why it's a different approach. We will be discussing it in more detail in some of the next podcasts. But to Sephora's question, it's pretty much the same. We use probability also, but just in a little bit different way. Okay. Okay. So a typical situation where you would prefer nearest versus optimal versus stratified. Now, what is typical situation for me? I can tell you that I typically would use 2 or 3 of them. So I would use, let's say, nearest and optimal to kind of validate the analysis from multiple angles. But if you would really have to choose, nearest is very good when you have a larger sample, right? When you can just afford to match patients one by one, and then some patients will be discarded. It's a problem that we have to address another way. But if you have a lot of patients, one-to-one organic, one-to-one patient per patient matching is then much easier. So in that situation, again, I usually don't choose between them, but if I had to choose, that's the situation where I would choose nearest. Now, if I have a sample, which is not ideal in terms of I cannot easily match patients one-to-one, I would then prefer to collectively match them using optimal, right? But again, I don't typically do this. I usually use both. Stratified, I use sometimes when it's appropriate, because stratified is not easy to implement always because we have to form these stratums. And again, we need very, very large samples for that. But sometimes it can be useful. And again, choice is usually dependent on how your data is structured, how much data do you have, and then how much one-to-one matching do you expect you can do. So you start with that, and then as you figure that out, you can then make a choice. But as I said, I usually use at least 2 of them in my analysis. Okay, so as we covered that, and thank you so much, Sephora. I think it was a very, very interesting question. And I encourage any question which may be related to this analysis. So there is still time. I will be discussing another topic now, but in case anyone is interested, you can ask any question you think is important to address, or maybe I missed during the podcast. Okay, going back to this, and this is really, it seems like an ending of the podcast, but actually it's not. This is actually the most important part of the podcast. And this one goes deeper than most people would think about propensity score matching. Most people actually do propensity score matching. They get some results, they interpret them, and they say, okay, those are the results. It doesn't work that way, at least not if you want to do it correctly. It's more like PSM and then what? Like if you do propensity score matching, you need to be ready to know actually exactly what you need to do next. So you'll get some inputs from the propensity score matching analysis, but regardless of that, it's very good to, regardless of your results, do some sensitivity analysis. As you mentioned before, there is the problem sometimes with the unnatural variance. If we use matching with replacement, there is the problem of unmeasured confounding. There's the problem of PSM paradox. Sometimes we could have other problems as well. There is the problem of sometimes choosing a wrong algorithm, right? So after we complete the PSM analysis, we have to address each of these. One of the best ways is to do sensitivity analysis. In that sensitivity analysis, we will quantify, very importantly, we'll quantify the unmeasured confounding and check if the unmeasured confounding is actually distorting the results in a way that could actually change our interpretation of results. So we need to see if our interpretation is correct. Then another very important aspect, I haven't discussed it so far, but it's very important. Whatever PSM analysis gives us as a result, we have to triangulate. We cannot just say, oh, this is the result. We have to try different angles. So we can try to do, for example, 3 algorithms of matching. We could try to do propensity score matching and weighting. We could try to do with different subgroups in a population. We could see if the subgroups affect the results. And very importantly, we need to interpret from multiple angles, right? There is also the domain knowledge that we have in the analysis. So we can use different methodologies, different angles, and domain knowledge, and kind of triangulate between them, try to assess the analysis from different angles, and see if they all point in the same direction. Are there contradictions between them? If there are contradictions, that is immediately a signal for us to see why that contradiction is there. How can it be explained? Do we have to analyze those contradictions further? And there are always additional considerations, right? So every PSM analysis is special, and there are always unique things about them. And now I mentioned some of the scenarios here, but it's important to understand that once you do a PSM analysis, it rarely ends just with the PSM analysis. You always have to, most of the time actually, you have to consider these additional considerations. That's very, very important. Okay, let me just check if there are any additional questions. No. So I will be closing the podcast workshop with this, and would invite all of you who have been participants in this one, who joined, listened in, left comments. I would like to invite you to the next edition, which will be next week at the same time, in which we will be discussing the external control arms. So again, want to thank you. I really appreciate you interacting and joining this session, and looking forward to seeing you in the next edition next Thursday, same time. Thank you very much.